Okay, first thing is first, I have to apologize. I have not completed the learning objectives. And I will get those done as soon as I possibly can. I really apologize that they're not ready yet. Um, but for the time being, just what I would do is I would try to kind of construct my own, like look at the PowerPoints and say, like, okay, what is the main point of what we're talking about here? Like I said, I'm sorry. Um, in addition to that, I don't have the whatchamacallit, the practice exam ready. But I expect that I will have both of those things done very quickly before our next class meeting on Wednesday. So I'm sorry about that. Yeah, I hate to say like, oh yeah, I'll do this by this time, and then to kind of let you guys down on that. So again, I'm sorry. Now, with that said, what we've talked about so far, we've talked about kind of some of the important parts about enzymes. We've talked about bisubstrate reactions as well as unisubstrate reactions. Now, we spent a good bit of time on bisubstrate reactions, and the reasoning is that your bisubstrate reactions account for most enzyme reactions because most enzymes are going to be requiring at least two substrates. And I kind of think about it as it brings two things in. It transfers a group from one of those substrates to the next. See something in that chat. I got to look at that. We have one more exam before the final. Yes, we do. So we've had three. I got the question of, do we have one more exam before the final? I'm going to go ahead and look at my calendar for you guys. We have exam number 4 on December 4th. So we've got, let's see, today is the 11th, 13th, that's 3, 6, 7. We have a total of 8 class meetings remaining this semester before that fourth exam. And then that fourth exam immediately precedes your final exam, which your final exam is December 9th. Now, I've mentioned this before, and I have, in case anyone's, if it feels like I'm belaboring a point or anything like that, but if you have any questions about um, grading and everything like that, then uh, please just let me know, and I can kind of get you squared on kind of what are the important things in terms of like performance and doing well in this class. And what I mean by that is like, well, if I do well in this exam, what are the implications of that? What are the implications of doing well in the final versus, not doing well in the final? How much does that hurt me and everything like that? So with that, I would like to go ahead and get cracking because we are talking about enzymes, but we're going to take a little bit of a, not necessarily a detour, but we're going to talk about one thing that I think is very important to kind of spend some time on, and that is enzyme inhibition. Now, enzyme inhibition is something that it's it's a really important thing. In order to do well in your understanding of enzyme inhibition, I would say the most important thing for you is to understand the Lineweaver-Burke plot. The Lineweaver-Burke, I'm going to label it as LB, is also known as your double reciprocal plot. Now, your double reciprocal plot is the plot that tells you basically how an enzyme catalyzes a reaction and gives you kinetic parameters, two important kinetic two important kinetic parameters of Km and Vmax. Now, these important kinetic parameters, well, what they've got, it this double reciprocal plot, for lack of a better word, it linearizes data, your enzyme data. Now, when it comes to looking at a plot like this, the important points on this plot are, I'm going to change colors of my pen. They are right here and right here. Now, your X and Y axis, your X axis for a double reciprocal plot is 1 over the concentration of your substrate, and the Y axis is 1 over your initial velocity of your enzyme catalyzed reaction. Now, with that, I use that phrase a lot. But considering that information, the important points on this plot that I pointed out give you your 1 over V max and the negative 1 over Km. So your y-intercept in a double reciprocal plot, y int is equal to 1 over V max. And your x-intercept is negative 1 over Km. Now, if somebody wouldn't mind adding to the chat, does the value for Km, does that have units? Simply yes or no, or thumbs up, thumbs down. Yes, perfect, it does. And the units for Km are a concentration. Now, I want you to think about that. And let me ask you this kind of follow-up question. If, a concentration, let's say good units for that would be something like nanomolar, micromolar, millimolar. These are all good units or good examples of, kind of physiologically relevant units. My follow-up question for you is, have you ever prepared a solution with a negative concentration? Or have you ever heard of a solution with a negative concentration? And I want you to think about what that would mean. Yeah, absolutely. No. I've asked that question before and people are like, ooh, that's an abstract, esoteric question. Ooh, yeah. No, it's not. You can't have negative salt in a solution. And so what I'm getting at there is this right here. People have a tendency to see this negative 1 over Km, and then they think, oh, okay, well, I'm going to do this calculation. And they end up putting a negative value in where they don't need a negative value, or they put a positive value where they don't. And then they come up with something like Km is equal to negative 3.6. And typically when they do that, they have not assigned a unit. And I think that it's helpful to always remember that, yes, Km is a concentration and it has units, because whenever you say negative 3.6 millimolar, chances are you're going to kind of have this like triggering event in your head and you're going to think, wait a minute, you can't have a negative concentration. So I say all that just so, whenever the moment comes where you're, looking at an exam question or thinking about that carefully, that you have that kind of last like security net where you think, okay, it can't be a negative value. Okay. The negative reciprocal. Right. Yeah. So you have this essentially, you have, whenever you plotted this data, let's say that you had something like -3 or -4, it doesn't really matter there. I'll put 4, just giving myself a round number. And you take this value and plug it in directly to this x-intercept. And so this would be -4 is equal to -1 over Km. And so those negatives cancel out. I think people have a tendency, and I know whenever I say people, I'm generally describing a younger Joel Gray. Younger Joel Gray had a tendency to see this right here and think, oh, okay, well, that means it's a positive. So even though I had a negative there, I should switch it to a positive. And then I'd come out with a negative value and I would fail to think critically about what that value means and what the significance of it is. Okay. I was, I had a tendency sometimes to just kind of memorize things. Okay. So does that answer your question, Morgan? Sorry if I kind of roundabout discussed it, but didn't answer it. Okay, cool. So let's go ahead. I've got a total of 3 top hat questions. I got 2 right off the top. When an enzyme has a single substrate, it will more than likely follow the pattern of substrate binding and product release known as. So these are our binding models. I'm giving 45 seconds for this question, just so we can kind of move through it a little bit more briskly. So start the question. Is this a ping pong model, random sequential, an ordered sequential, or none of these? We got about 6 seconds left. We got 41 answers, 42 out of 45. That's pretty good. Let's see, can we get, yeah, we got 45 out of 46. Okay, let's look at the right answer. Okay, so this is the key in this question was a single substrate. When we have a singular substrate, none of these models actually apply. And I don't want you to think that I was lying to you guys or anything whenever I asked this question. I don't want you to think I was deceptive by intention, but all of these, a ping pong model, a random sequential, and an ordered model, they all are models for bi substrate reactions. So this would be E plus A yields EA plus B yields EAB. And this is basically our completed ES, enzyme substrate complex. Okay, so just to kind of keep on your toes with respect to that question. So none of those are actually applied. We don't really have a special fancy name for single substrate reactions. We will talk about allosteric enzymes, and allostery does apply for some enzymes, but random, sequential, ping pong, and ordered all apply for bisubstrate reactions. Okay. Now, next up, and let me clear all my drawings. If in a bisubstrate reaction, an enzyme transfers a functional group from a substrate onto itself, then transfers that group from itself onto a second substrate. This is a good example of blank. Okay, so let's go ahead and visualize this. We've got our enzyme plus our first substrate. I'm going to label that substrate A. Okay, now let's just imagine that, well, A has, I'm going to draw carboxylic acid. Okay, and from this, we get E with that carboxylic acid. Okay. Now, my first question for you, whenever you answer this, is E equal to, is this a true statement? And you don't have to answer it in the chat, just think about it. And then my follow-up question is A with that carboxylic acid equal to, and I'll just label A. Think about these. Are they the same? Yes or no? And now I'm going to go ahead and start the question. But what we're looking for is one of those terms. Is it the bisubstrate, or which of the bisubstrate terms applies? Because the implication here is that this E with the carboxylic acid is then able to bind the second substrate. Okay, I'm going to clear all my drawings out. All right, go for it. A few more seconds left. All right, we are done. Okay, so essentially, yes, I can do it. Good job, guys. So we got 36, so 82% answered correctly. So the key here in a ping pong reaction and in this description is that the enzyme has changed. Something about the enzyme has changed, like a functional group has been added to it, and it's been added from the first substrate. And only then is that new form of the enzyme able to bind the second substrate. So in our schematic that we looked at, we had E and F. F is the kind of the new enzyme version. And E is kind of the original form. Okay, so great job on that. Great job, guys. Okay, now we'll proceed onto our discussion for today. So, we're going to talk about inhibition patterns. Now, an inhibitor is just what you think it would be. It's a compound, it's a molecule that basically prevents an enzyme or interrupts an enzyme from catalyzing a reaction. Now, I have this tendency whenever I'm talking about inhibitors, I say inhibition and inhibitor. I say them with a different cadence and I sometimes stumble over those words. So, our inhibition patterns. Inhibitors act in a variety of different mechanisms. Now, they all have unique names. Now, an inhibitor may bind at the same site as one of the substrates. So it may. Now, what is implied there is it doesn't always. Now, inhibitors structurally, the ones that bind at the same substrate binding site or the substrate binding site, they structurally resemble the substrate. So they look similar to it. So, you were talking about an inhibitor of glycolysis or an inhibitor of a hexokinase. Well, it's probably going to be a six-membered ring. Now, an inhibitor may bind at an alternate site, affecting catalytic activity without affecting substrate binding. So, if we think about our Cleland notation, we have our enzyme and our substrate. So this first model right here, well, E and S, I'm going to say may form, but may also not. Now this right here, an inhibitor may bind at an alternate binding site without affecting substrate binding. So in this case, ES will form. Okay, next up, many inhibitors are capable of doing both. So our most common types of inhibitors, and these terms get a little bit confusing, or they can get a little confusing. We've got a competitive inhibitor, we've got a mixed or a non-competitive inhibitor, and there's subtle differences between a mixed inhibitor and a non-competitive inhibitor. And then last but not least, there's an uncompetitive inhibitor. Okay, now what I want you to take away from this and these three types is that non-competitive and uncompetitive are not the same. It's very tempting to think that they are just because they seem like they're kind of replaceable terms, but linguistically and biochemically, they are different from one another. Okay, linguistically, they might be interchangeable, but in terms of what they do at the molecular level, they are different from one another. Now, here we go. Our patterns of inhibition. The first type of inhibitor that we want to look at is a competitive inhibitor. Now, a competitive inhibitor, well, it does what you would think a competitive inhibitor would do. It competes with a substrate for the enzyme substrate binding site. So to think about what we just said, that ES complex may or may not form in the presence of a competitive inhibitor. So here's our Cleland notation to kind of show what is happening. Okay, now I'm going to switch to my highlighter. What we've got at the top, E plus S. Okay, so we're familiar with E plus S going on to either to form ES, and we've got our K sub 1, our rate constant for the formation of ES. And then we've got K sub minus 1 for kind of the dissociation of ES into E plus S. And then we got our K sub 2 to basically be our rate constant for the production of our product. Okay, so that's like the ideal situation. Now, in the presence of a competitive inhibitor, that competitive inhibitor is denoted right here with the capital letter I. We have what is known as a Ki, a rate constant related to the binding of our inhibitor. Now, if we have these three components in the same solution, we could kind of look at it as our enzyme is, it's almost like our enzyme's flipping a coin. What's it going to do? Is it going to bind the substrate or is it going to bind the inhibitor? We don't know. Now, when it comes down to which is it going to bind, well, one component of that is you have an affinity. Basically, does the enzyme want to, and not want like a preference, like a to personify it necessarily, but chemically, what types of interactions are existing between the free enzyme and the substrate versus those interactions between the free enzyme and the inhibitor. Now, in the event that the enzyme binds to the inhibitor, so it has a greater affinity for binding the inhibitor than it does for the substrate, we're going to form this EI complex. And that is the enzyme and inhibitor. They basically locked up with one another. Your free substrate is still in that solution. Now, just like we saw over here with our enzyme substrate complex being capable of dissociating and reforming the enzyme and the substrate, the EI complex can also dissociate to form the enzyme and the inhibitor. Okay, now I'm going to erase all that. Okay. So, one of the important points of this is affinity. The kind of chemical composition, the amino acid composition of the substrate binding site. Does it give more of a preference for the substrate or does it give more of a preference for the inhibitor? It's a great question. That's an important question to ask. Now, if we were to imagine that our enzyme has an equal affinity for the substrate and the inhibitor, then you're flipping a coin basically. Um, it's almost like which is it going to bind? Now, if you're I always like to think about this as, I think about like a candy or something like that. Let's say that, and to kind of take it from an approach of a, a layperson statistics. I'm the layperson on the statistics here. Let's say that your enzyme is going to bind either an M&M or a Reese's Pieces. Um, Tell me in the chat what are the shapes of Reese's Pieces and M&Ms, and I'm talking about plain M&Ms, are they different from one another? No, they're pretty much the same. Okay. So let's say that you had a Ziploc bag. Here's my Ziploc bag. And in that Ziploc bag, I've got M&Ms denoted by these red circles. And then I'm going to go with orange because Reese's Pieces can be orange. And let's see, there's four. Okay, I've got four of each. If I put my hand into this bag, I'm going to use my hand here. If I put my hand into this bag, what are the chances that I pick up a Reese's Pieces versus an M&M? Do I have an equal chance of getting a Reese's Pieces versus an M&M? I don't really, you know, if my hand kind of has an equal preference for this, I can't remember the name of the shape for these candies, but this kind of like oblong circular candy, there's an equal number of each of them. My hand's going to go in, pick up one of those candies, and it's basically, sorry, how many did I count? I got like I think 1 out of 8. So I got a 1 out of 8 chance of picking up a Reese's Pieces, unless my counting's wrong, sorry, and a 1 out of 8 chance of picking up an M&M. Okay. Now, if let's say that I wanted to, and let's look at the M&M as my substrate and the Reese's Pieces as my inhibitor. That's right. I got a private message that it's a 50-50. Absolutely right. Okay. Now, if I wanted to, let's say, shift it in the favor of going in this direction, what could I do to increase the likelihood that I'm going to pick up an M&M or pick up an M&M is a metaphor for my substrate. What could I do to increase the likelihood that I'm going to pick up that substrate? And, let's just think about this bag. And I'm not changing my hand at all. I'm not looking in the bag or anything, but I can change the contents of the bag. I've got a, I just got a private message. You would need to add more substrates than inhibitors. You're absolutely right. I could add more M&Ms. And so think about the competition. We've got a competition between my M&Ms and my Reese's Pieces. If I increase the amount of my substrate, increase the amount of my M&Ms, then my enzyme, my hand, is more likely to pick up those M&Ms than it is to pick up those Reese's Pieces. So I'm effectively getting, shifting or tilting the favor towards binding the M&M by increasing the concentration of the M&M. So when you're using a competitive inhibitor, that's one of the things that you can do. With a competitive inhibitor, well, kind of adjust the parameters of the competition. So increase the likelihood that you're going to bind that substrate by adding more of it. And this is something that biological systems do, is they will produce more of the natural substrate in an effort to outcompete something. Now, that's our first form of inhibition. And I would say that a competitive inhibitor is the type of inhibitor that most people kind of can wrap their mind around pretty easily. Okay, now our next type of inhibitor, or our next type of inhibition, is known as an uncompetitive inhibitor. Now I'm going to draw a line and I'm going to make a point to not delete this line. I'm going to look at my Cleland notation and my definition. So a competitive inhibitor and this kind of model right there. I have an uncompetitive inhibitor. The uncompetitive inhibitor binds the enzyme substrate complex. So effectively, things that you can take away from this is it doesn't bind E. It doesn't bind the free enzyme. And instead, what it's going to bind is the ES complex. And we see that right here. Only whenever the substrate has bound does an uncompetitive inhibitor say, oh, I want to bind that. And so when we compare these two, well, it's almost like we have the ES complex. And with a competitive inhibitor, as soon as we form the ES complex, we can look at it as, yeah, we're going to make our product. We're good. With an uncompetitive inhibitor, when you form the ES complex, you can't really say that because you kind of have an equal chance of forming the product or the inhibitor, or sorry, the inhibited reaction. And when you form that ESI complex, sure, that can go back to ES and release the free inhibitor and go on to make the product. But this is kind of like I always kind of think about it like a holding cell or a holding phase, a holding station. You're not going to go on to directly form that product. Instead, you have to kind of walk back a step and then form your product. So when you look at these two models of inhibition, I think that there's a tendency, and it's a perfectly fine tendency to look at them and think, oh, well, one of them's better than the other. And of course, you're thinking about it from a perspective of effective inhibition. But if we think about a competitive inhibitor, when we wanted to basically negate the inhibitor, we just increased substrate concentration. And more substrate would basically compete with the inhibitor and dilute out that inhibitor. Over here, with our uncompetitive inhibitor, if we upped the substrate concentration, well, where is the substrate? It's over here. We have no problem with the substrate concentration because that's going to basically get us to forming our ES complex. So if you increase the substrate concentration, with an uncompetitive inhibitor, that's not going to really have much of an impact on your reaction and whether or not it's catalyzed. So I'm going to add a little detail out here that is adding more substrate does nothing. That was my best reference to the Big Lebowski. If you've ever seen that movie, there's nihilist in there. They believe in nothing. So that was my best there. Okay, now that's an uncompetitive inhibitor. Okay, so we've got a competitive inhibitor that we can compete with, and an uncompetitive inhibitor that forms an ESI complex. Now, what I think is really valuable for understanding your different models of inhibition is to think about um, the different complexes that can form. Well, can the EI complex form with an uncompetitive inhibitor? Nope. Can the ESI complex form with a competitive inhibitor? Nope. They go they basically approach the enzyme in different ways. So they attack it differently. Now, a very fair question that's probably on the tip of your tongue is, well, is there an inhibitor that does both, that attacks the free enzyme and attacks the enzyme substrate complex? And the answer is yes, there absolutely is. It's known as a mixed inhibitor. Okay, now I'm going to draw a line to kind of, again, isolate the uncompetitive inhibitor, our mixed inhibitor. Now, a mixed inhibitor is a type of inhibitor that basically binds to both the free enzyme and the ES complex. So you could kind of think about a mixed inhibitor as the best of both worlds. So, in terms of looking at an inhibitor and thinking about it like the most effective, is it which is the most effective, which is the best? I think there's a tendency to lean towards that mixed inhibitor because, well, then it's going to have two different mechanisms to stop the enzyme from catalyzing the reaction by forming the EI complex and the ESI complex. Now, when it comes to like a physiological perspective and a physiological question of, well, which is the best, you know, it's it's more nuanced than that. You can't really say, oh, well, this is the best across the board. Um, for some therapies or for some kind of disease states, it might be best to use a competitive inhibitor, and it might, in others, be best to use an uncompetitive inhibitor because you do have to think about, well, what is this ESI complex? Is that going to just kind of float around and oxidize a bunch of stuff? Is that going to cause damage? Is that going to present a problem that the body is going to or the cell is going to struggle with? So it's a little bit more complicated than that. Now, when it comes to these different models, which we're going to take a deeper dive into all of them over, the remainder of today and then on Wednesday, a very real and good question to ask is, well, how do I decipher between them? I see these models and I see, okay, well, EI and ESI, if they both form, that's a mixed inhibitor. If EI only, that's competitive. ESI only, that's an uncompetitive. How do I discern between them? How do I, you know, determine? Because, you might be thinking, oh, well, if there was a way that I could measure the concentration of EI, I could say, oh, well, it's there or it's not there. What about the concentration of ESI? Well, it's there or it's not there. If you could do that, then maybe that would crack the code. And you're not wrong, but it's a little bit more direct. And, what I started talking about at the beginning of this class was this is a very important topic to have a good understanding of the Lineweaver-Burke plot. The Lineweaver-Burke or a double reciprocal plot is going to be very valuable for understanding your different types of inhibition. Now, how do we distinguish between them? We make an inhibition plot. That inhibition plot is similar to our initial velocity plot, but we use an inhibitor instead of a second substrate or a third substrate, as it would be. Now, what we get from this are different patterns. So what we get from this are different patterns, different binding patterns. Now, what I want you to think about is, when we were putting together a Michaelis-Menten plot, which if you remember the Michaelis-Menten plot, it looks a little bit like this. Your x-axis is labeled as substrate concentration and your y-axis is your initial velocity. One of the things that you have to keep in mind is in studies of an inhibitor, and let's say substrate, enzyme, and then let's say initial velocity. Okay, so here's what you're going to be looking at. In studies of inhibitors, I want you to, I'm not going to, let me just move this real quick. Um, so over here on the left-hand side, I'm making a table that shows experimental trials. And I'm going to label them T1, T2, T3, and last but not least, T4. Okay, so from each one of these trials, you're going to have an enzyme concentration. And I'm just going to keep it simple. One, 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 one. You're not going to change the concentration of your enzyme. Your substrate concentration, that is going to gradually increase, which is what you would see looking at this x-axis. You're going from 0 to infinity effectively. Your initial velocity, your v sub 0, well, that's going to be reported, and chances are it's going to increase as well. Now, to limit the confusion, I'm just going to keep this as dash, because that would be a result that you would read out. Now, when it comes to your inhibitor is going to have a fixed concentration, 2, 2, 2, 2. And your inhibitor's concentration would be something like millimolar, nanomolar, whatever. So for all of these trials, you're going to get different data points. And you're going to plot those data points. Now, what I want you to take away from this table is that your enzyme concentration and your inhibitor concentrations remain constant. What you're varying is your substrate concentration. If you want to evaluate, do another trial where you look at your enzyme's influence or your inhibitor's influence, well, then you would do another set of trials where you would increase your inhibitor concentration. Now, all of this is going to be very valuable because what you're going to do with this, and does anyone have any questions actually before I proceed? We're going to go do one more top hat question, and then I'm going to get into competitive inhibitors. Does anyone have any questions about these? What about non-competitive inhibitors? And will we get to that later on? Morgan, that's a fantastic question because non-competitive inhibitors are kind of a derivative of mixed inhibitors. So it's almost like we group mixed and non-competitive together because they're both capable of binding and forming the EI and ESI complexes, but your non-competitive inhibitors have a tendency to bind and form one of those two complexes. So I'm starting out right with this slide as mixed, but as we kind of scaffold through competitive and uncompetitive, and then when we get to mixed, we'll kind of break that out and say, what does a mixed inhibitor look like and what does a non-competitive inhibitor look like? So to answer your question, we'll get to that a little bit later, but for right now, think about that as kind of like it's a flavor of a mixed inhibitor. Great. Are there any other questions? Okay, I'm going to go ahead and clear all my drawings. And we've got our next top hat question. We've got 45 seconds for this. And this is just a reflection on that. All inhibitors bind to the same location on an enzyme as the natural substrate. True or false? I think I've got the timer. Do I have the timer? Yes, I do. got, I always like an absolute style question because my inclination is to say no, just because, yeah, that's my inclination. The correct answer is false. So all inhibitors do not, because if we look back at the previous slide, we saw that there are some inhibitors that they bind in a location different from the substrate because the substrate has to bind. Any sort of uncompetitive inhibitor, for example, well, the substrate binds. So an inhibitor cannot bind in that location. It has to bind somewhere else. Okay, so we're looking pretty good there. Now, a competitive inhibitor. Well, a competitive inhibitor is going to compete with, and I think what we'll do today is we'll look at a competitive inhibitor plot and then kind of call it a day. A competitive inhibitor competes with a substrate for the enzyme, substrate binding site. So basically the same place that the substrate's going to go, that's where the competitive inhibitor wants to go. Now, if we look at, as an example, the enzyme succinate dehydrogenase, this is an enzyme that is involved in the Krebs cycle or the tricarboxylic acid cycle. And the natural inhibitor, or sorry, the natural substrate for this enzyme succinate dehydrogenase is succinate. Now, if we were to think about this enzyme from what we've talked about a little bit previously, well, this would be an example of a oxidoreductase. So this is an enzyme that a dehydrogenase is kind of your clue that it's an oxidoreductase. Um, the inhibitor for this enzyme is a molecule known as malonate. And if you look at succinate and malonate, you've got carboxylic acid, carboxylic acid. And then the difference is basically the length of that chain that connects the two. They're very similar to one another. One of them's a little bit smaller, and so that blocks the reaction from taking place. Whereas in your normally catalyzed reaction, succinate is going to be converted to fumarate. Okay, so that's just a good example of a competitive inhibitor. Now, we talked about this a little bit previously with respect to, well, what can a competitive inhibitor do and how can a competitive inhibitor be kind of undone? So a competitive inhibitor reduces the amount of free enzyme available for substrate binding. Okay, so the amount of kind of for all intents and purposes, the concentration of the enzyme goes down because it's getting, and this is a trend that you want to pay attention to, it kind of gets sequestered off into this EI complex. And what that leads to is increase of Km for the substrate. Now, thinking about the Km and your P50, well, if your Km goes up, similar to your P50, if your P50 goes up, what does that mean for affinity? If the Km goes up, what does that mean for your enzyme's affinity for the substrate? It decreases. You're absolutely right, Morgan. Great job. So how do we navigate that? How do we deal with that? Well, one way that the cell does it, and we can do it in an in vitro setting, is we can increase the substrate concentration. We basically increase the substrate concentration and in effect kind of outcompete the inhibitor, leading to the formation of the ES complex. The effect of a competitive inhibitor can be overcome with high concentrations of the substrate. So up the concentration of your substrate and you kind of negate that inhibitor. Now, here's what a competitive inhibitor is going to look like. Good, we got 5 minutes. Here's what a competitive inhibitor looks like and a Michaelis-Menten plot. Okay, so let's look at this kind of olive-colored curve. This is, a series of trials where we've increased our substrate concentration. And what this is showing on the x-axis is basically, we know what the Km is, approximately, and then we just double it, triple it, quadruple it, multiply it by 5, quintuple. We're just increasing our substrate concentration by magnitudes of Km. And what you see is at some point you're getting very, very close to your Vmax. And, there is definitely a gulf between your Vmax and that top of that line, but don't Don't fret about that. Okay. Now, in effect, if you think about E plus S yields ES, and that's going to lead to P plus E, product formation. Effectively, where is an a where is a competitive inhibitor going to impact? It's going to impact over here. So as soon as you form ES, you can go on to form the product pretty easily. So your Vmax won't change. And so effectively, this line right here, this kind of navy blue colored line, well, this is where you have basically a second trial where an inhibitor is present. And what's going to happen is if you extrapolate this out far enough, it's going to, and this is, I don't like this illustration for this reason, but when the inhibitor is present, you're going to get to the point where your enzyme's maximum velocity is achieved. And then when you double that inhibitor concentration again, you're going to get there. It's going to take a lot of trials and it's going to take a lot of your substrate, but you're going to get there because with a competitive inhibitor, the Vmax will not change. Now it's a little bit easier to illustrate this point with a LB or a Lineweaver-Burke plot, where you take the data that's over here and here, and you plug it in as reciprocal values. So 1 over initial velocity and 1 over substrate. Here, our blue line, kind of royal blue, depicts whenever the inhibitor is absent. Well, that graph is going to give us a Vmax at this y-intercept right here. And it's going to give us a Km. Let's call this -4. So that would give us a Km when we say -4 equals -1 over Km. We're going to get Km equal to 0.25. Okay, then we got our green line. Our green line is our magenta line. Let's call that negative. I'm going to call that -2. And then this is -1. Km for this goes from um, goes to 0.5. And then our magenta line is Km equals 1. And the way that I solve that, these numbers I just kind of arbitrarily made up. I made them relative to one another. There's -4. This is approximately -2. This is -1. So I kind of just put those numbers in as fillers. And then I said my x-intercept is equal to -1 over Km. And so I said -4 equals -1 over Km. And that's where this Km, and that's where this 0.25 came from. And then subsequently, -2 equal -1 over Km. That's where this came from. And that Km is going to be, or sorry, that's where this 0.5 came from. And then -1 equals -1 over Km. That's where this Km equals 1 came from. So what we see is our Km increases. Our Vmax remains the absolute same. That's what's taking place with a competitive inhibitor. So a competitive inhibitor isn't going to slow the reaction down. It will prevent the reaction, but as soon as that ES complex is formed, your product's going to be generated. And it's going to be generated basically at the same rate it previously was. Okay. It is 9:50 right now. So what I'm going to do is I'm going to clear my drawings. We're going to pick up with this on Wednesday. And so if you have any questions, I can stop